Now let's look at actual phase calculation. So the first, actually the example we want to do it is the roasting process calculation. So as we can see, the original mineral we want to use in this calculation is the 1 kilogram of the minerals, which is 866 gram of CuFeS2 and 57 gram of the FeS and 77 gram of SiO2 as input. Okay, and then we're going to inject air, and then we'll do the calculation at 600 degrees Celsius. So I already set up those calculations here. So let's look at one by one. Okay, so first of all, the database selection. So as I mentioned, we want to use the PACT-PS, FT oxide, and FT miscellaneous database. And this FT miscellaneous database containing sulfide mineral, FT oxide, of course, containing all the oxide minerals, and the PACT-PS containing gas species. So we need all these three databases. So yes. And then we are injecting one by one all these species. And the unit here, by the way, if you click this actual unit, actually the tab by using the mouse left click, then you can see that this is Celsius and ATM, and then Joule and the gram unit. Of course, you can use the more engineering unit like a kilowatt hour or some other actually value, sorry, and say okay. So now you are entering all these species, and you may ask me, okay, do I have to really enter CuFeS2? Why not just enter copper, iron, sulfur, and nitrogen and oxygen in the calculation? Yes, if you want to do simple equilibrium calculation to look at the final state, then you don't have to worry about the original mineral form. You can just simply use the element, if you like, as input. As long as you actually have the mass balance, there's no problem. But if you want to see the energy difference between the initial state and the final state, the initial, actually the mineral, the phase is very important. Depending on the phase, you have different amount of energy actually assigned for the phase. Okay, so that's why if you want to use the initial condition like this, and if you want to really calculate energy change between input and output, then you had better use the actual species and with each phase and the initial temperature simultaneously to get the more accurate energy balance calculation. Okay, so that's why we're adding the mineral CuFeS2, the chalcopyrite, 866 gram, and the 57 gram of FeS, and 77 gram of SiO2 like quartz. And then all this one is the following the same unit as a gram. Here, I want to actually use the oxygen and nitrogen because this is gas phase. I want to use the unit instead of the gram. I want to use the as mole. Then what you have to do is you have to enter this mole, MOL. So for example, I'm adding here 0.79 A. A is the variable, and so anything inside of this bracket, you can use the linear equation of the A. So 0.79 A or 0.79 minus 0.1 A, whatever it is, but it should be linear equation of the A, and then you can use the A as a variable and change actually the value of your input. And then if you simply just put it like this, it will be 0.79 A gram over N2 is entering. But if you want to change this one as a mole, basically you want to overwrite your unit, then you have to say small mol at between the space between the amount, then it will actually consider this one as a mole. Okay. So here I set up basically simple air condition 0.79 and 0.21 mole of nitrogen or oxygen. And some of you might ask me then, okay, so the gas is stream. So I mean N2 and O2, if you want to consider as air, then you have to make this one as the stream file first at 25 degrees Celsius, and then you have to enter as a stream actually the file. Yes, it is true. Theoretically, yes, that would be the better way to actually treat this N2 and O2 as air actually stream. However, for the current actually the calculation purpose, because this is we want to actually use the initial condition to do the energy balance calculation. So air, the N2 and O2, both of them is a gas phase, and gas is typically ideal solution. So either you enter it as a separately like this, or you enter as a solution, gas solution as a stream. The enthalpy value is same, because that ideal solution assumes that there's no reaction enthalpy no enthalpy of the solution between the species. So the enthalpy as a separate actually phase, separate species like this, or as a solution, as an air solution, the enthalpy is same, because the enthalpy is controlling the energy we want to, the energy, enthalpy is the energy we want to actually look at in the end of this process. So that's why I just entered as N2 and O2 as separate actual species in this case. Okay, at 25 degrees Celsius. That's good. And then you go to the next. And then now you have to do the phase selection. So if you actually go here, select, for example, all solution, then it will take all solution from FT miscellaneous and also FT oxide database. And sometimes there's something not selected because there's the slag AB question mark option, and then typically we are by default taking the first one as the most accurate actually the solution you can take. Okay, that's why it looks like something is not actually taken or not actually selected, but it doesn't matter because the among three we have to select one. Okay. Now, as I mentioned before, because this is at the low temperature at 600 degrees Celsius, so we know that there's no liquid phase existing, and so it's more phase diagram type of the calculation. So it's better to not use actually this method, because this method was for the smelting or converting process, liquid state. So you have to take this one out, and liquid copper is same thing because this is liquid state, and iron liquid never be formed in this condition. So it's better to take off these three, and also this FES is inconsistent with the rest of the sulfide phase we actually have in the FT miscellaneous database. So you can take it off even this one. So you take off this 4 in this calculation. And solid and gas phases, you can select all the phases. And sometimes there's the custom selection like this. And because if you do the mouse right click on top of this one, you can see that there's a lot of the duplicated phase. So some of them is selected, some of them is not selected, depending on the priority of the database we set internally between the database. So SiO2 is existing both in the packed PS database, for example, and then also FT oxide database here. So we select SiO2 from the FT oxide database instead of the packed PS database. In this way, we can remove the duplicate. Okay. Sometimes if you have the duplicate, there might be some strange actually the phase transition, which is not real actually phase transition. Okay, so that's why we preset the priority of the database for you, so you don't have to worry about it. You can just simply click, then it will do all the phase selection automatically. Say okay, so that's what it is. And then you set your final temperature, final pressure, and then A is the variable in moles. Basically, it's moles of the air. So I'm setting from 0 to 50 by every 1. Okay, and then calculate. Then you have the result like this. So we have the result like this. And so for example, when you go to the 10, okay, so I have this is the input, okay, and then this is the amount of gas phase, and gas phase, if you look at it, there's 0.8 moles of N2, 0.16 mole of SO2. That's quite high amount of SO2 already. And then there's all other phases. And then there's the 827 gram of CO2S and MES, and this is typically CO2S rich phase, as you can see. And then about 2 gram of the spinel phase, and spinel is oxide. And if you look at it, there's a lot of iron plus minus sign here. This is all modeling species in the thermodynamic model we are using in the spinel solution. So you don't have to worry about this one. The overall composition you have to look at is actually from here. Okay. So whenever you see the solution, there's the system component. Actually, as you can see, this is the actual composition you have to compare with your analysis. So iron is 0.72, or in terms of mole, 0.428, and the oxygen is 0.57. Okay, and that's the amount of the iron and oxygen mole in the spinel solution. And this is in fact Fe3O4. Okay, and then there's 0 moles of the pyrrhotite, 0 moles of the degenerate, and etc. All of them is 0 in the end. And then there's a little bit amount of SiO2 solid too. Okay, so it is okay. So, and then one thing you can also look at it here is when you go down all this calculation result, at the end of this result, you can see the energy value. So there's the delta H and H, delta G, and Gibbs energy. So H, Gibbs energy, volume, and etc. So all this value is the absolute enthalpy at your current state. It means at your 600 degrees Celsius, when A equal to 10, your system enthalpy is this value right now. And your Gibbs energy at the current stage, at the 600 degrees Celsius, this one, and etc. And this delta H, what this delta H means then? So this delta H is only shown in the result when you select initial condition in the input. So this delta H is H at your final temperature, 600 degrees Celsius, minus H at your initial condition at 25 degrees Celsius with your input mineral. Okay, so that's delta H. So this shows you the energy balance basically. So when the energy is the positive, it means you have to inject this amount of energy to the system to maintain to keep your final temperature, to make your final temperature 600 degrees Celsius. So you have about 26 kilojoule of energy required to make your final temperature at 600 degrees Celsius. That's what it means. Okay. And then if you go to the, for example, 11, I think, or 15. So for example, if you go to the 15, your delta H would be now negative. Okay. So now it means this is exothermic reaction, sorry. So you are producing this amount of the H in the calculation. So it means you have to take out this amount of H to keep your 600 degrees Celsius as a final temperature. That's what it is. Okay, so once you have this kind of result, you can check one by one, but sometimes it's too much information, so it's very difficult to see all of them. Then you can simply go output and then make a plot the result. Okay, you have to decide your axis. So for example, you can decide your axis like, for example, sorry, let's move a little bit. You can select your axis, for example, y variable as gram, okay, gram, and the x variable as alpha, and then refresh. And I want to take the gram of the old actually the phase which is forming in this calculation. Say okay, and then so gram of what, and select. Okay, and then you can select, okay, select button here and select the all stable phases. So it can automatically select what kind of phases what kind of phase have the more than 0 amount, and there's 8 species, and say okay. And now if I plot, then you can see the result like this. Okay, so this is amount of alpha, the air amount in mole, and this is gram of the different species. So you see there's MS, it's a Cu2S kind of the phase, and then there's the gas phase, and there's this one. If you click it, you can see that this is pyrrhotite, and then this one is spinel phase, and this is the degenerate phase, and then SiO2. So as I said, at 10, you actually you convert all the pyrrhotite to the spinel and some other phase. Okay, So the 10 is actually something we can look at it in this roasting process condition. Okay, and then you can do also some other calculation, some other plot. So axis, y-axis. So now I want to, for example, I want to plot, let's say enthalpy, as we've seen before. So delta H, energy change, and refresh and OK. And because the energy enthalpy is not depending on the species, it's a system actually the value. So you don't have to select any species, and then you can simply plot. Then you can see the result like this. So depending on the alpha, you can see actually the H change here. So H equal to 0. This is when you actually energy balance becomes 0. So, and above this one, you have endothermic reaction. Below this one, you have exothermic reaction. You need energy to maintain temperature. You have to take out the energy to maintain temperature. Okay. So as we discussed in the presentation, we want to actually take about this condition when A equal to 10 as a good roasting condition. Okay. So let's close it and close it. So this actually value 10. Okay. At 10, so this is the roasting product. So this gas is probably going away. And then if you look at it here, there's the CUS, MES kind of the phase, spinel phase, and then there's also some SiO2 solid phase and etc. Okay, so I want to take these three solid phase as input for the next calculation, the smelting calculation. So either you can save one by one all this one as a stream file, or you have to write down each number, and that's most stupid actually thing. But you can save each of this one as output and then go stream file, save stream file, and then take one by one like this way. And this is, I mean, you need at least 3 times. You have to do 3 actually you have to make a 3 stream file like this, and it takes time. So one of the easy way to do actually this kind of saving the stream file for the next calculation is simply go here and then recycle all stream. Then you can actually take all the output of this result, all the product of this result as input for the next calculation. Okay, let's try that. Recycling. Okay, as you see 100% of the spinel coming out, and this 100% is so if I take it, it is about 61 gram. Okay, CO2s 827 gram, and gas phase 332 gram, and etc. Yeah, so this is actually most easiest way to save actually a stream for the next calculation. So recycle all stream file. Okay, now so let's move on to the next one. Okay, so we finished this one. Now we want to do the smelting process. As you see in the smelting process, I take all the input from the recycling except for the gas phase, and then I'm going to add nitrogen, oxygen, and SiO2. Okay, and the amount of SiO2 is 10 gram, and the A equal to 0 to 50 gram. Okay, so 0 to 50 moles. So let's try to add this one again. Okay, so here, so now I'm injecting more, 3 more actually, and the first one is nitrogen, and then oxygen, and the last one is SiO2. Okay, and this one was 0.64A mole and 0.36A mol. So as I told you, we want to use the oxygen enriched air in this calculation, and then this is B. So P is constant, A is the variable. Okay, we don't have to worry about the database selection because we didn't close the actual system, or we didn't start the new calculation. So this is the same as the original. Okay, and then the unit is same too. Okay, so the initial condition is actually activated here, and this one is okay because it's all from the 600 degrees Celsius. But I want to enter this one from 25, then you can click 25, and it will change all 25, as long as you have the same stream number. And if you want to change the this temperature is different, then you have to change this one as a different stream, and then you can change it also different temperature if you like. Okay, or if you want to keep the same one, then you can use the same stream number. Okay, that is okay. Then let's go to the next one. And then now this is the phase selection, because you didn't change that much of the all the element, so the phase selection is same as before. But I don't like this phase selection because in this case we want to do the calculation at 1200 degrees Celsius, so it means I'm going to have liquid copper or matte probably. Okay, so the rest of the actual phase should be removed instead. Okay, so what do we have to do? Then select clear all solution, for example, and then go, and then select all solution from FT oxide database. That's okay. So we select all from FT oxide at least, and then in the FT miscellaneous, I'm taking only copper liquid and the matte, and for example, these two. Okay, I don't like the other one. That's okay. And then all the solid phase and all the gas phase. Okay, and the P was 10, and A was 0 to 50, every one. That's okay. So this is what we want to calculate. And then if you do the calculation, we have the 51 calculation result here. So again, let's go to about 24, for example, 24. And then you have 30 moles of the gas, and you have 75% of N2, 24% of SO2, a lot of SO2. In fact, the copper actually, the company, they actually produce a lot of the sulfuric acid. And because all this sulfur, which is SO2 gas coming from their roasting and smelting and converting process, is collected internally, and then they are making H2SO4 kind of the solution. And this is the byproduct of the copper industry. Okay, and then if you go down, you have the 382 gram of the matte, and then you have the 286 gram of the slag, and then you have even 192 gram of the spinel phase, etc. Okay, so we have three things: matte, which is about 77% of the copper, it's very high copper, and we need only about 60% here, as I said. And then here you have SiO2 and some other thing, okay? And then you have the copper oxide is about 1.4%, okay? And more problematic one is this one. You have the too much actually spinel solid phase, which is not very good for your tapping process. So we have to check actually the best condition. So the one of the best one, one of the easiest one to do it is go to output, plot the result. So I want to see actually the overall phase change. So axis, and then now when you go to the axis, y-axis as a gram, okay, with alpha. Refresh, say okay, and select all stable phase. That's good. Say okay, and then plot. Then you can see the result like this. Okay. Depending on the alpha amount, the gas amount, this is the amount which is changing with the change of the old phase. Okay, so you have slag, matte, gas, and spinel, solid spinel, and etc. So here, from this to this range, you don't have any other solid phase, only slag and the liquid matte. Okay, that's good. So, as I explained, about 16, A equal to 16 is the good condition for this calculation. So let's just close it and then look at it again. So A equal to 16 here. Okay, so SO2 and N2 and SO2. And then if you go down, this is the matte, 498 gram of matte, 59.2% of copper. It's quite high actually copper grade, good enough. And then 382 slag, gram of slag, and 22% of SiO2, about 70% of the, it's very good actually, the matte. And then you have about the slag, and then you have about 1.3% of CO2, and then all the rest is 0. Okay, so I like this one, so I'm going to save this. I'm going to use this math for the converting process, for example. Okay, so once you believe sometimes this calculation is very good, I want to utilize this one, I want to use this one in the future again, then what you have to do is, what you can do is, you can go here and you can save actually this input and all the calculation condition as actually the file here. So a clip file. So save as. You can say that, okay, this is, I like it, so it's a copper smelting process, for example, something like this. Okay, and then save, and then you can say the copper process at 1200 degrees Celsius, for example. Okay, and then whenever you do some other calculation, you can just say new, and then you do all the calculations. So everything is gone, and but after probably a couple of months or a year later, I want to actually redo this calculation. And sometimes you cannot remember what you have done, but you can actually go open, and then you can find actually that one. So that was the copper smelting process. This is the one I just saved. Okay, and then open it again. Then it remember everything as you did last time. Okay, it's cool, yeah. So in this way, you can simply go change some number here and then do the same calculation again and again. Okay, so you can actually get the consistent result in this way. Okay, so let's go back again. The calculated result, we say that 16. Yeah, so this math is the math we want to actually save for the next calculation. Okay, so what I can do is, you can recycle everything again, or you can save only this math. So in this case, let's simply just save this math for the next calculation. So what you have to do, output, and then you can go save stream file, save stream file, save solution, and then only math like this. Okay, and then you can save actually the math for the next calculation. Okay, so that's what I explained. That's what I also explained to you. So we have done this actually, the saving actually, the process. Then we go to the converting process now. So what I want to do is, I actually take actually that math I did the calculation before, and then adding some additional amount of SiO2, and then also adding additional actually the air here, and then do the calculation at 1250 degrees Celsius. Okay. So I already actually saved this one. So let's look at it. Open, and then one of the calculation I did is converting first process here. Yes. So this is exactly how I save it and then reopen it. Okay. So I have the math, which actually coming from the 1200 degrees Celsius. Okay. And then I have SiO2 addition B, and then N2 and the O2 as a 0.64 moles of A, 0.36 moles of the A in mole, and then initial condition. So the math is coming 12 degrees Celsius. The other one is inserted from the 25 degrees Celsius. And database selection is same as before. And next. Then you have everything set up, and then again, I'm taking only copper liquid and the math solution from FT miscellaneous, and all the FT oxide database is selected same way. And then I'm setting my temperature at 1250 degrees Celsius. I'm setting B as a 50 gram in this case, and changing the A amount from 0 to 10 and average 0.5, and then do the calculation. Then you have all these results. Okay, so when you go to about 6, for example, I think this was what you want to see, and we have the N2 and SO2 gas still coming out. A lot of SO2 is still coming, and then we have 376 gram of the math, which is about 77 actually percent, which iron is 1.5%, which is still quite high. we want to reduce this ion lower than 1% for the converting second stage of the converting process. So this is a little bit high. And then we have slag phase and then some other phase. Okay. And so in order to actually check this one very quickly, also we can do output, for example, plot the result, and then axis, and then y-axis. And so look at it. What I want to do is now y-axis as weight percent. Okay. So it means I want to see the weight percent of the copper, iron, sulfur inside of the my math database. Okay, math solution. That's what I want to see. And refresh and say okay. So weight percent of what? You have to go phase selection here. Okay. So this is the N2 element. And then this is copper liquid. So you can select this one, or matte, copper, iron, sulfur, iron, copper. So you can select these three, for example. This is good. But most of the time, I'm recommending you, instead of using this one, sometime actually you can see some weird kinds of the species here, because this is modeling species. And so, for example, here, as you can see, spinel, there's the Fe3O4 1 minus phase, Fe3O4 1 plus phase. And this all this charged actually the species is so-called end member of the model, and which we are using for the modeling. Okay, so this is sometimes not actually the species you want to select, and so the species you want to select, the element actually you want to select is typically using the very end of the actually your tab here. Okay, so for example, if you scroll it down in the very bottom, then you can see that there's the old element here, and there's gas phase, copper, iron, and etc. in the gas phase. And then this one, CuLq, with copper, iron, and etc. And then met, so copper, iron, sulfur, silicon, oxygen, nitrogen. So this is actually the species I want to see. Of course, in this case, silicon, oxygen, nitrogen is not existing in the math, so this value is 0. Okay, and say okay, and then plot. Then you'll see the result like this. Sorry. So here you can see the amount of the gas phase, the air in mole, and y is the weight percent of species in solution. So this is copper, sulfur, and iron in solution. So iron, if you double click, you can see that, okay, 6.5, so 6 is 1.5%, 6.5 is 0.49, so 6.5, or if you go 7, 0.14, and 7.5, 0.08, so it keep going down, okay? So at least, if you want to have at least less than 1%, it should be 6.5 or above. That's why we can see it here, okay? So this is the element. And then also now, if you go axis, we can also see the overall species in gram, okay? And say okay, and go select. You can unselect everything, clear everything, and then you can select all stable phase, and say okay, and plot. Let's look at it again. So if you look at this result, so gram and the alpha, and so here, so this is CuLq start forming, which is not good, and this SiO2 is all gone. So somewhere here we can actually probably have the good condition. So somewhere about 6 to 7 probably you can have the most ideal actual condition. Okay, now let's close it, and let's close it, and so let's go to the 7. Okay, so I have 0.14% of iron, and the copper is 80%. Okay, that's good. This is our target. And then we have this amount of the slag phase, and there's some loss of the copper. And as I told you, this is not very good actually, the thing. But nevertheless, we are not adding any additional other fluxes like CaO and some other thing. So probably this is unavoidable. And then we can have all the rest is 0. Okay. So And you see this kind of slag is typical pyrolyte slag. So FeO and SiO2 ratio is equal to about 2 to 1. Okay, so that we call it as a pyrolyte slag. Pyrolyte slag. And then this is the map which is required for the second stage of our process. So you can save this one. Again, output, stream file, this stream save stream file, and the map as for the next stage. Okay, then we can actually save this. We can use this one for the second stage of calculation. So good. So now we go to the second stage. So we bring that one in, and then we are adding some additional species and do the calculation. In fact, I also already made that one. So first stage, you see, and then I have converting process somewhere below. Oh, it's not there. Yeah, here. So, no. Yeah, this is the one. So, I made actually, again, I saved actually the stream file, okay, from the previous calculation at first stage, and then adding small amount of SiO2, and then N2 and the oxygen again from 25 degrees Celsius. Almost same, except for the med is new one. Then go next one. And then I have all the result here. So again, I'm selecting phase selection, only taking Cu, Lq, and the met from FT miscellaneous, and everything from the FT oxide, and etc. Okay, and 1250, and this B is the extremely sensitive because we have a very small amount of iron still remaining in the met here from the first stage of the converting process. So I did many different calculations, and then I found 0.3 is quite reasonable value. So I'm adding only 0.3 gram of the SiO2, and then changing the oxygen, the air amount from 0 to 10 moles, 0.5. Then do the calculation. And then if you look at all this one, at 6, for example, you can have still again very high amount of SO2 is producing, and you have to collect that for the sulfuric acid generation. And then you have the kappa, which is like 99.3%. And then you can see there's sulfur, and then there's the oxygen, and then iron is almost 0. So there's this two is the main impurity in the kappa here. And this kappa, we call it bleached kappa. Okay. And then there's small amount of liquid slag is forming like this. And the kappa amount inside of this slag is a little bit high, but nevertheless the amount is very small, so it's okay. And all the rest is all 0. Okay, so this is actually the final bleached kappa we want to produce in this converting process. Okay, and you can save it this one again as a stream, and then you can go to the, for example, refining process if you like. Okay, so this show you briefly how we can use the flex age calculation from the roasting process, and then smelting process, and the converting process. The one of the key you have to think about in this kind of the calculation is saving the output as a stream and then entering to the next one as input. Okay, so that's actually the key to make this flow sheet type of the calculation. Okay, and also, I mean, in terms of research, I think while you are doing this kind of the calculation, you see that different kinds of the flux amount changed actually your calculation result. So if you consider all this flux amount and then injecting the gas amount, and depending on actually your original mineral, you have to design the different kinds of the flux amount, and then changing all those flux amount, you need a different amount of the optimum gas amount, and all this one is combined together, and then this is the key to evaluate the cost of your process. Okay, so in terms of cost evaluation, this kind of the calculation will be extremely helpful to set up the new actually process. Okay, so if you have any question, you can always contact me again. Okay, thank you very much.